And then if we use a reducing lens next to the, right in front of the focal point, it'll straighten the light beam back out, and it will make that wide beam of light going in, narrow beam of light going out, and function as a telescope. But the problem is, this is a reducing lens, and so you're looking at your primary mirror through a reducing lens. And so if you looked at the objective without the eyepiece in place, this is the way it would look. But when you look at it through the reducing lens, the objective looks a whole lot smaller. And yet there's a magnified image in there, but the objective lens looks so small that your field of view is really small. It's like, you know, your thumb at arm's length, tiny, tiny little field of view. So not long after this design came out, Johannes Kepler figured, how about if we let the light from this magnifying glass cross and come to a point and start expanding again, and then use another magnifying glass to project this narrow beam of light. And you know, what that'll do is you're looking at your objective through a magnifying glass instead of through a reducing glass. And the difference is dramatic. This is what you get with Galileo's telescope. This is what you get with Kepler's telescope. And so, you know, the downside of Kepler's scope is that the image is upside down. And Galileo thought that was unacceptable. So he continued using his design, where Kepler thought, well, you know, I don't really care if I'm looking at Mars right side up or upside down. And so Kepler continued using his design, with the result that if you see a Galilean telescope today, it looks like this, because nobody's built much since the 1600s, because the design just really wasn't very useful. If you see a Keplerian telescope, it looks like this. Pretty much any refractor you see today is going to be a Keplerian design. So Kepler's design really caught on, whereas Galileo's not so much. So this is kind of what we would call a normal telescope, the Keplerian refractor. This is what people think of when they think telescope. Trouble is, these simple objective lenses had chromatic aberration. Around the edges of the field, you'd get the stars would break into colors, because the different colors of light would come to focus at different points. So they learned pretty quickly that the shallower you made your objective lens, the longer the focal length and the less chromatic aberration you did. So that led to some pretty unusual designs. So here we go, we're gonna get into some weird stuff. This, Johannes Hevelius's 140-foot long telescope. Look at that thing, you know, the scale of the people down here looking through the eyepiece at a scope that's 140 feet long. I can't imagine that was very successful, but they actually did that in order to reduce the chromatic aberration. Christian Huygens, he built an open air telescope that basically just used a rope between the objective and the eyepiece. And there's a little bit of a stick here for aiming, and there's a little stick there to keep the aim straight. And, you know, he could raise it up and lower it, and he could walk around in a semicircle down here for aim. I guess it worked. I don't know. I doubt that it worked very well, but they were doing that in order to try and eliminate chromatic aberration. So it didn't take long before somebody figured, hey, you know, if we use mirrors, light reflects to a point without any aberration, or without a chromatic aberration anyway. And James Gregory figured this out in 1663, which was, you know what, 50 years, not even 50 years, like 40 some years after the invention of the telescope. So the idea of a reflecting telescope came along pretty early, but nobody had the skill to find these mirrors. And if the you know, if the skill level had been a little higher back in that day, then the Gregorian telescope might have actually taken off. But it wasn't until what, 1770, what did I say? 1673 that it was actually built. And there's one in a museum. You know, they're not very common. The most common Gregorian telescope you'll see today is actually a radio telescope, the Arecibo telescope in, was that Puerto Rico? it's a Gregorian. The light or the radio waves come in, hit the primary, bounce up to the secondary, and bounce right back down to the collector in the middle of the dish. But in the meantime, Isaac Newton came out with his design, which just totally eclipsed the Gregorian design because it's so simple. It has a single primary mirror that's parabolic in cross section, a flat secondary that bounces light up to an eyepiece, and Newton let the light cross the focal point and then put the eyepiece beyond it, just like Kepler, so that you got a wide field image. And Newton built an actual scope to prove his design out. Now, the interesting thing about this, the thing I love about it, is that it was only a 2-inch diameter primary mirror, so the scope is only 10 inches long, but it was enough to prove the concept, and it worked really well. But what I love about the design here is you can tell he screwed up the placement of the focuser. He had to plug that hole and put the focuser in its proper spot, and it just warms my heart to know that Isaac Newton and I both have the same problem when we build telescopes. And also, notice that he mounted it on a ball mount. I think that was a brilliant design because that's what I came up with too. But it didn't catch on. The ball mount did not catch on for many, many years. Instead, people started building just weird, unusual things. I call this a guillotine mount. I'm not sure what it actually is called, but the back end of the telescope rides in this little cradle that goes up and down on a block and tackle, and it'll slide down this track if you get toward the zenith, so that the bottom of the scope will actually tuck in close to the front and get you up close to the zenith. There's little cranks here and here and here for raising and lowering and moving left to right. It's on wheels down here, so you can get gross motion by just pushing it around. And William Herschel, one of the most famous astronomers of all time, used this kind of a mount in the late 1700s and into the early 1800s. So, this kind of mount, we would look at that and call it a kludge. It was actually the type of mount that was used even 100 years after, almost 200 years after the invention of the telescope. And you get to larger scopes. This is William Herschel's 40-foot telescope, 49.5-inch aperture, 40 feet long. It's what we would call an alt-azimuth mount, sort of, in that the scope raises and lowers in altitude along, with this block and tackle, this enormous block and tackle that, somebody back here pulling ropes, and then this whole platform goes around on wheels. The whole telescope platform, including the building, move in azimuth. And this was kind of state of the art back in those days. Pretty cumbersome. Lord Ross's Leviathan, the 72-inch scope in Ireland, I think it was. You could only move it in altitude just a little bit. This was the observing platform, so you could move it a few degrees, and you could rotate it left and right until it hit the walls. That was your azimuth choice. That's what they had. In 1824, the German equatorial mount was invented, and that became a standard for any scope that would fit on an equatorial mount. Cave Astrola Company kind of pushed the boundaries a little bit. They started building scopes 12, 13, 14, even 16 inches in diameter, and putting them on equatorial mounts. And they just got really big and cumbersome and very hard to maneuver. Sometimes your eyepiece would be pointed at the ground. You'd be crawling under the never mind. And you'd be crawling around under the telescope. Good Lord. Okay, here, I'm going to throw this into another room. Okay, off you go. And okay, so where was it? Yeah, equatorial mount, but they're cumbersome. So we'll move on to John Dobson, who looked at these alt-azimuth mounts, and he looked at cannons on the battlements of castles, and he thought, why in the world don't we make a cannon-style alt-azimuth mount? And the scope rises and falls on this altitude axis, and it rotates around on the azimuth axis. And that idea comes so well that basically any common Newtonian telescope today is mounted on a Dobsonian mount. I mean, I have a hard time finding a Newtonian that's not on a Dobsonian mount, unless it's a little cheap hobby killer that's still put on an equatorial mount. And they got larger and larger, and somebody figured out, well, we don't need the tube anymore. We can just use struts in between the top end and the bottom end. And so now truss tube Dobsonians are fairly common. In the day, when they were first designed, they were kind of unusual, but now they have become quite common. But Newtonian optics are still basically at the bottom of pretty much any reflecting telescope. There's primary mirror, secondary mirror, and eyepiece. On this scope, this is just my scale version of Astroscan, because I like to build ball scopes. And but down inside, it's still just Newtonian optics all along. But the problem with Newtonian scopes is even a parabolic primary mirror isn't perfect for reflecting light to a point. Well, it is to reflecting light to a point in the center, but the farther from the center you get, the more coma you get. The image stretches out, and you get more blurring out near the edge. So people are trying to figure out, what do we do to get rid of this coma? And they thought, well, how about a parabolic primary, a hyperbolic secondary, and bouncing light back through a hole in the primary, and that gives you a long, effective focal length in a fairly short package. They went back to this idea of the longer you make it, the less aberration you've got. So there was that, and Cassegrain scopes were fairly popular for quite a while, but they didn't solve the problem completely. The Schmidt-Cassegrain is an interesting variation on that, in that the primary and the secondary mirror are spherical, which makes them very easy to make. You can grind a spherical mirror easier than pretty much any other kind. But the Schmidt corrector plate that corrects for the coma and the astigmatism caused by the spherical primary and secondary, that was very difficult to make until a guy named Tom Johnson figured out how to pull a piece of glass onto a metal plate that was bent in the right curve. He vacuum deformed the glass and then ground the glass flat. And when you let the glass spring back into shape, you get the corrector. And so the Schmidt-Cassegrain became a fairly popular scope. A Russian named Maksutov figured how to do it with all spherical surfaces. If you have your corrector plate spherical and your secondary mirror just painted on the back of that, you can have a spherical primary. And so Maksutovs are very common too. But one thing all of these things have in common is that they are very, very long focal length telescopes. That helps decrease the aberrations. And also I should point out, this corrector up in front dews up very quickly in cold weather and humid conditions. So you wind up with dew on the front of your telescope. So somebody thought, how about if we put all the glass just in front of the mirror, right in the back of the telescope? So there's a glass lens, essentially, and this red line here is the mirror behind it. Apparently it works, but for some reason or another, it never really caught on, except Mangan mirrors are kind of used in other designs, like the Klevtsov, which you've probably never heard of, and I hadn't either until I started doing this research for this. But it uses a parabolic or maybe a spherical primary, and it puts some corrective lenses in front of the secondary. And this secondary lens here is a Mangan mirror. Apparently that's pretty good for correcting aberrations, but again, very long effective focal length, so it's not a very wide field telescope. The real game changer was when two guys, Ritchie and Crétain, came up with the design of using both a hyperbolic primary and a hyperbolic secondary. Very, very difficult to grind and polish and get the right shape. But when you get it, it's nearly coma-free all the way across the field of view. So the result of that is that nowadays almost any professional telescope is going to be a Ritchie-Chrétien, or we call them RCs because it's really hard to pronounce Chrétien. Okay, so like the Keck telescopes on Mauna Kea, they're RCs, and they use a segmented mirror. I don't know, you can't really see it down here very well, but that's 36 hexagonal mirrors all stacked together down in there, and all together they create a hyperbolic primary. The Hubble Space Telescope is probably the most famous Ritchie-Chrétien telescope in the world, or off the world, as you might think. Problem with RC telescopes is you still have to have a structure to hold the secondary mirror in front of the primary mirror. And that structure creates diffraction spikes. And also, anytime you have a secondary mirror in front of a primary mirror, it reduces the contrast. So people have been looking for ways to avoid that pretty much since the beginning of telescopes. And actually, William Herschel came up with a design. He didn't do it because of the contrast problem. He did it because his mirrors only reflected about 60% of the light that hit him. They were called speculum mirrors, and it was just a polished piece of metal that didn't coat it with anything. So, you can imagine how reflective is a spoon, say, and that's how reflective his mirrors were. So he tried tilting the mirrors so that the eyepiece, or maybe the secondary mirror or just the eyepiece, was out of the light path. But the problem, of course, it wound up with not only coma, but astigmatism, because a tilted mirror angles the light. You can imagine light hits the far end of the mirror. It's got a longer path to get there than it does to get to the near end of the mirror. So it doesn't come to a focus at the same point. So somebody thought, well, what if we just use a chunk out of a mirror? Let's carve this part out of a larger mirror. The secondary mirror would normally go right here. Well, it's almost out of the field of view of the primary if we only use a part of the mirror. And here's a side view of what we're talking about here. What happens if you do that? You don't have that secondary obstruction, but you still get coma. The sweet spot is now way up in the corner of your field of view, and then the coma extends all the way across your field of view. It's actually worse than if you just use a regular Newtonian design. So that didn't fly very well. But people kept thinking, well, the key to fixing chromatic aberration and the key to fixing coma in the early Newtonian designs was just to make them really long. So what happens if we make a really, really long reflector? And they came up with the Schiefspiegler. The light comes in, it hits this primary mirror, bounces off a couple of other mirrors, a secondary and a tertiary, and goes up into the eyepiece. And, this is a real photo of a real Schiefspiegler. And Mike Curtin is actually going to make one of these. He's working on the mirrors right now. So, can be done, and the results are pretty cool. But it's a very, very long focal length, narrow field of view. Some variations on that. The YOLO, the mirrors are actually not ground parabolic. They're distorted with pressure and ground spherical, and then they spring back into the correct shape. It works, but holy cow, it's hard to do. So you need a machine shop and a lot of patience to make a YOLO. Schiefspiegler just uses a regular parabolic primary, a flat secondary, and it uses these corrective lenses, which are tilted at the same tilt as the primary, to kind of undo the damage from having a primary mirror that's tilted. And it actually works reasonably well. This is kind of a design that a lot of people have settled on, but you got two mirror surfaces and two lenses that you're running your light through. So there's quite a lot of loss there. And it's also a very narrow field of view because it's such a long scope. So, in the end, it just didn't really pan out, trying to make these scopes really long. Here's one that I like just because of the picture of the two guys standing next to it, and they've actually traced the light path on the scope. So it comes in, hits a primary, hits a secondary, hits a tertiary, hits a quaternary that bounces it out to the eyepiece. That's the eyepiece right there. And the neat thing about this is the eyepiece stays put as you tilt the scope up down in altitude, and even as you rotate it around in azimuth, it kind of stays put. So it's a neat design. It's called a Naismith design when you do that. And here's another Naismith, same basic idea. Probably not quite as many mirrors. I think it goes all the way down to primary, back up to a secondary here. It might go all the way to a secondary there. Yeah, of course it would, or there'd be no reason for that tube. And then back to a tertiary and out to the eyepiece. So that works pretty well. Long focal length though. Here's a short one where somebody actually carved a hole in the side of a Schmidt-Cassegrain to put their camera there and made a Naismith mount out of it. And I think anybody who cut a hole in the side of their Schmidt-Cassegrain telescope's got to have a little bit of moxie. I'd kind of like to meet that guy. Well done. A lot of professional telescopes have what's called a coude flat down inside. And this mirror can be turned and angled. So if the scope is moved to a different part of the sky, this mirror can compensate and aim the focal point down to an instrument that's actually just sitting on a tabletop. And the instrument stays put, and the focal point is always there because this coude flat can rotate to put the focal point right into the instrument. And I think when Bernie gave his talk about the Mount Wilson, where was it? I've lost it. Anyway, wherever he was working down in Arizona, I believe it was, or New Mexico, they had a coude focus on the scope he was working with. And he was shining a laser out of the focal, from the instrument port, shining a laser into that and bouncing it on out to the moon. And that's how they figured out the distance to the moon, using that coude focus. So we're about done with bouncing because it gets pretty crazy after this. Edwin Herrig, I think, wins the competition for the most crazy design of bouncing light back and forth and back and forth and back and finally into the eyepiece. Wow, that's all I can say about that. That is an unusual telescope design. So I think it's the craziest one I found, but I did find a bunch of others. So here we go. You can use refractors and make as many bounces as you want, starting with the lens over here on the right-hand side. And then, the lens brings it almost to a focal point, so you can use a tiny little mirror down here. And then the light beam is expanding back out and hits this mirror, which, by the way, is a Mangan mirror, and then down to a tertiary or quaternary, and then it bops it down into the eyepiece. And this has actually been made. Here is an 8-inch version of a Schuppmann, and it's at Stellafane. I think they have that there in their observatory, and they use it every year at Stellafane. And it goes on and on. But there are a bunch of other kind of interesting, different kind of designs too that don't just involve multiple bounces. So I'm going to move on into that. Anybody have questions at this point? I haven't heard any. I hope I haven't ignored anybody. But if you have questions or anything, just unmute your microphone and shout them out. So here we go. This is like the second, we're well over halfway, and we're getting into the last portion of it, but I've got a bunch of slides of really odd. Starting with, let's go right back to the very basic thing. What do you need in basic Newtonian anyway? Well, you need a place to put the primary mirror. You need a secondary mirror that will bounce light into a focuser, which is in this photograph directly behind the secondary. And so I built one of these. It's a 2x4 with a piece of plywood down there. And I use this as my test rig when I'm star testing a mirror that I'm working on. You notice this mirror is not coated yet. It's still just glass, but it reflects enough light if I aim the scope at Polaris. And that's what this prop is for. Props the scope up at just the right height to look at Polaris. The scope's not good for anything else, but I can aim it at Polaris, and since Polaris doesn't move much in the sky, I can put up crank up the magnification and looking through the eyepiece that's behind the secondary, I can look at the image of Polaris and star test my my mirrors. So that works pretty well. So that's about as basic as a telescope can get, and still function. This one's one of my favorites. David Davis, the guy with the bullhorn here, made this 13-inch f3 mirror, and he was really proud of the mirror. But David is not a real telescope guy. He doesn't do much observing. He just wanted to show off the mirror that he created. And this is up at Oregon Star Party. And he decided, well, he needed to build a telescope to put the mirror in. And so like the day before the Star Party, he got a bunch of this, I call it Pink Panther foam. It's insulation that you'd put in the walls of your house. And he cut it into strips, and he taped them all together, and he shoved them down into a barrel, which is, I think, is a planter like you put on your back deck. And cut the bottom out and mounted the mirror. You can see Mel is holding the mirror mount, goes down under there. Dave made that scope just as a test bed for this mirror, and he made it in less than a day, which I think that qualifies as a rather unusual telescope design. But he's inspired me to create my own secondary cage out of foam when I needed a really light secondary cage for one of my scopes. So it works. Craig Daniels, another local Oregonian, he's decided, why do we always make telescopes in tubes anyway? There's no reason why it has to be a tube. Let's make a big old box. It'd be like building a coffin. You can use fencing boards, and it works. And he props it up on a leg, just like my star testing rig. Only his has a little screw thread here, so he can raise it and lower it by turning the screw. And it's on little wheels down here, so he can roll it around in altitude or in azimuth. And notice there's no focus here. There's just an eyepiece stuck in the side of the box. Well, that's because he focuses it by moving the primary up and down on a sled. This threaded rod goes all the way up to the top of the scope, and there's a knob up there that he can turn, and it pulls the primary up and down. And that's how he focuses. And works like a charm. He does his astronomy with this scope all the time. And a mutual friend of mine named Lott, he's the guy who builds finders. That's one of his homemade finders up here. He took that idea of moving the primary and he thought, what can I use as a shuttle to move the primary back and forth? He took the platen, or the carriage rather, out of a typewriter. This is out of an old like Underwood typewriter. And he has a little ratchet down here that essentially activates the little escapement mechanism that, when you type on a typewriter, those of you old enough to know what a typewriter looks like, the platen moves in little discrete little motions. And so as you turn that knob, his primary mirror kind of moves in a discrete little clink, clink, click, click, click. And yes, indeed, he left the bell in. So if you get too close to the end, it goes ding and warns you that you shouldn't be getting any closer to your secondary mirror. And he reports that worked pretty well. Taking the boxy side of Craig Daniels's Dodgson scope, Mark Yonker built this scope using boxes. And for travel, this box goes down inside that box, this box goes down inside that box. The whole unit turns 90 degrees and drops down inside this box. And it's just a great big cube. And it looks really kind of odd, but there's a 12-inch Steve Swayze, like 10th wave primary down in there. I've looked through this telescope. It's got one of the best views I have seen in a homemade telescope. I mean, it is a fabulous scope, although even Mark will admit it's kind of funny looking. So Mel took that idea of the 13-inch f3 mirror and made a very high quality mirror. Basically, I think Dave Davis's mirror was kind of the inspiration for this. But he built this fabulous, fabulous telescope. He calls it a zip dob, and it folds up. The secondary cage folds down in, and then all of these joints here fold up to where it can be carried like a suitcase. And it's got its little ground board and flex rocker down here. And he used that for many years and loved it dearly. And just recently sold it to Lauren Wingert, who is watching right now. Hi, Lauren. And yes, you have probably the coolest scope in this presentation, except possibly the next one, which is the 25-inch that Mel scaled up the zip dom to just see how far he could go. And this is a test bed for a 30-inch that he plans to build. And one of the things I love about this 25-inch, this one's f2.6, is a very, very short focal length. Notice how Mel is hunkering down a little bit to look into the eyepiece of a 25-inch telescope pointed near the zenith. I think that is pretty cool, especially when you realize that that telescope is resting on something new down here, something a little bit extra, and that is what he calls an alt mount, in that the normal telescope motion, it slides around on the rocker in azimuth or in altitude using this bearing. Well, he just created another one at 90 degrees to that. So this is another altitude bearing. And so when you get near the zenith, you can just push the scope in any direction you want, and it'll tilt this way or that, and it'll tilt this way or that. And you don't have the problem that's called Dobsonian telescope is actually quite difficult to aim straight up. This scope does not have that problem. And I will point out, I got permission today to reveal that Mel has now sold this telescope to Mark Yonker, the guy who built the nested cube scope. So Mark now has probably the coolest telescope in this slideshow. You never know. There might be others. Let's see. This one's pretty cool. This is a guy in Norway, I think, Sweden, one of those Scandinavian countries with the funny names. But he built what may be the smallest package for an 8-inch travel scope. It fits in his hand. I'm going to back up just so you can see. This little box holds that telescope, and you can tell, yeah, down here at the bottom is that's the box top that becomes the ground board. The box bottom becomes the rocker box. And altitude bearings are small enough to fit down inside the box when it's closed. 8-inch mirror, the struts, everything fits inside that box. So Mike Curtin and I are busy building one of these. Yeah, it's too cool to not build one yourself. Okay, I had to throw my own scope in. This is my round-bottomed trackball telescope with a basic Newtonian design. It's got a primary mirror down here, secondary mirror up here, bouncing light out to the eyepiece. My biggest contribution to this design was designing a tracking system where this motorized axle turns and moves the ball opposite the Earth's rotation, so it tracks. So that's my contribution to it. It is still considered unusual because it never caught on. I think there might be a dozen of these in the world, and I've made about half of them.
And that's a Home Depot bucket up top?
Yes, True Value. Yeah, that's a 5-gallon bucket with the bottom cut out. I think that's one reason it never caught on. People just went, oh, really? But it works. I have to say, it works really well.
Hey, Jerry.
Yo. Yes.
Back up to that Norwegian scope or whatever, the 8-inch that fits in the suitcase.
There you go.
The suitcase. Does that hold the eyepieces in there too?
It does. Everything. The finder, the eyepieces, everything. Even the shroud, which is made out of felt, and that's what protects the mirror from the other parts.
Wow.
I think, yeah, it's just impressive. I've been meaning to build one ever since I heard about it, and it's been a couple of years now. I've got the mirror done, so now comes the hard part, right?
So the tubes must collect
They have what do you call them, ferrules that fit down inside the tube, and they actually screw together. And he said, it's rigid as a rock. He can pick the scope up by the secondary, and it doesn't flex. Yeah. So, okay, so maybe that's the most impressive telescope in the show. Who knows? Okay, so moving on.
How much it weighs?
Not much, like 6, 7 pounds maybe. Yeah, I'm sure the mirror is the heaviest part. So getting on to the next kind of phase of unusual scope design, what I find interesting is that the creator of the original telescope, Hans Lippershey, he applied for a patent and was denied because the patent designers or the patent examiner said, well, people have 2 eyes. You know, it's not going to be useful unless you build 2 side by side. And so he never got his patent, which I thought was really kind of weird. But the patent designer was in fact correct. People do have 2 eyes, and when you use both eyes in a telescope, the view is significantly better. You get a 3-dimensional effect, and all that software in your brain that's processing the images, it really enhances the view. So this is the 12-inch, about f4.7 binoscope that I made, and it's kind of weird looking, boxy. But here's an even weirder one. This is Frank Kapansky's Popeye, in which Frank realized you didn't need to have 2 mirrors of the same diameter. You just needed to have 2 mirrors of the same focal length. And that's what he had. He had a 12-inch f6 and a 10-inch f7. And he made this scope. The 12-inch mirror is over on this side, down in here. And the 10-inch mirror is over in this side with a smaller hole. There's the hole for the 10-inch. The 12-inch, actually, the light path extends clear out into space over here, and the secondary mirror is just mounted on this flat panel that cuts right through the light path, just the way the center of a normal secondary spider would do. If you're having trouble visualizing the light path, here's an image that might help. The telescopes are just set side by side, and the farther one away from the eyepiece just has a larger secondary mirror, and it bounces the light right across the light path of the nearer one. And down here, this is looking straight down the tube. You can see it just bounces the light right through the light path of the other scope to an eyepiece. And that way you only have 2 mirrors per telescope again, instead of having to have a 3rd mirror. So it cuts down on the light loss. Very simple design. It works very well. Frank's made several scopes like this, and you know, they work like a charm. So moving on to talking about, okay, yeah, I used a bucket for the secondary cage of my scope. This guy named Brent Burton had heard the term light bucket, and he thought, I wonder if I can build a scope out of nothing but buckets and a primary mirror. And he succeeded, pretty much. These are actually flower pots, and this is an Ace Hardware bucket. These are drink cups from Olive Garden, plumbing fixture in there. But what he did is he took the optics out of a Star Blast, the 4.5-inch Star Blast, put it in here, and it works. So, you know, I just threw that in because it's weird and different. And here I threw in to prove that Brent can make a beautiful telescope too. This is the same 4.5-inch or 4.25-inch optics out of a Star Blast with some exotic woodwork. But Brent doesn't win the prize for exotic woodwork. I think Norman Fulham probably wins that prize. Norman makes the most beautiful telescopes I have ever seen. You know, you can just look at that, and the detail work is just incredible. You know, you've got the altitude bearing is a moon, and you know, the eyepiece rack is this kind of twisted, distorted thing. You've got these weird twisted struts holding the cage on. You know, laminated light and dark wood. It's just gorgeous. I've always been inspired by Norm. He's probably done 20 or 30 scopes similar to this, and never the same thing twice. So yeah, he wins as far as I am concerned, as far as just sheer beautiful. And also he makes fabulous mirrors. So these scopes are very high quality too. Getting weirder happens if you pour a cup of coffee, right, and look down into it. The water or the coffee flows out to the side, right? Well, it turns out when water spins, it creates a perfect parabola once you get the spoon out of it. And so what these guys have done is they have poured a couple of gallons of mercury into a very shallow pan, and they spin the pan. Actually, they spin the whole thing. The whole triangular arrangement spins, if I remember right. And it doesn't spin very fast, half an RPM or so, but the sides are, the mercury is squished out to the side and it creates a parabola. And a parabola is what you need for a telescope mirror. It's only good for looking straight up, but it's surprising how many things cross over a telescope in any given night, in any given year, as you wait for the seasons to change the tilt of the Earth's axis back and forth. You can cover 46 degrees of sky, actually 47 degrees of sky, if you just wait for the proper moment for the object that you're interested in to cross over. And this was a professional astronomy telescope that was used for many years, and it worked. So liquid mirror, that's one of the cooler things, I think. We're getting toward the end here. I'm looking at the clock and realizing coming up on an hour and coming up on the end. So just a few more. The infrared telescope that's built into a 747 so that they can get it high enough above the moisture in the atmosphere, because moisture absorbs infrared light. So you get it up into that high dry air in the stratosphere, and you can do infrared observing from well, not from the ground, but from Earth, rather than having to do it from space all the time. So they actually just built this into a 747 and they fly it around in the stratosphere and it works like a charm. You get up that high and the air is really stable, so the plane's not bouncing around. And the scope's probably mounted on shock absorbers anyway. But they do this quite often. This plane's in the air any good night that they can afford the jet fuel, I suppose. We are going to send an infrared telescope into space any day now, right? The latest plan that I've heard is that they'll launch this thing in 2021. So maybe next year, this scope will actually get off the ground into orbit, and it will become our premier space telescope, optimized for infrared observing, where we can look way, way, way back into the beginning of the universe when the light that was emitted back then is reaching us as infrared rather than regular visible light. We also can look at very, very long radio waves. This was one of the very, very first telescopes designed to look at radio waves. And it's basically a great big dipole antenna that's on a wheeled platform, so it can be rotated around in a circle. And that gives it a little bit of directionality. It doesn't have altitude directionality, but it does have azimuth. And, Jansky could move this telescope around and pick up radio sources. He picked up the sun and Jupiter, and I don't think he did Centaurus A because that can't be seen from New Jersey. But there are a lot of radio sources in the sky that he was able to pick up. This is, I think, my candidate for most beautiful radio telescope in the world. This is in the Ukraine, and it's just a set of fixed antennas, and it can be phased electronically. They can listen to various antennas at various times in order to get some directionality out of that. And just these weird little loops of wire, but that's a telescope. And here's a microwave telescope that's basically just a portion of a parabolic dish. Very extremely fast focal ratio, about f1. It bounces the light sideways almost. Well, it is sideways into the control room where they've got their instrumentation. And this is the microwave observatory that discovered the cosmic microwave background. So probably one of the most important telescopes ever made, a microwave telescope. And since the observing port is off to the side and rotates around with the telescope, I think this might technically be a Naismith design, although I'm not sure. I'd have to look that up. Radio telescopes can get pretty good size. This is in England. It's only the third largest steerable dish in the world, but I think it's the coolest looking one. And you look at that and you think, okay, yeah, that is a telescope. Different, weird, but even that is not the largest. The Very Large Array in New Mexico is made of individual dishes that can be moved out on tracks. This image shows them all packed in fairly close together, but they can be moved out to where they are 13 miles away from each other, the farthest ones. So it makes, in effect, a radio telescope dish 13 miles wide, with a lot of gaps in between. It's like if you were to throw a tarp over your mirror and just poke some pinholes in the tarp, you would eventually, I mean, you would get light through it. You would get an image, but, not very bright. Well, this is what they've done for radio telescopes. They spread them way out to get an effectively very, very large mirror, which gives them a high angular resolution. So they can use this to detect, stars orbiting a black hole at the center of the galaxy, for instance, and things like that. So moving into the other end of the visible spectrum, or beyond the visible spectrum, X-rays are very, very short wavelengths. And one of the things about X-rays is if you try and bounce one off of a regular mirror, the X-ray goes right through the mirror. X-rays will only bounce off of something if they make a very, very shallow glancing blow. So they make X-ray mirrors with almost cylindrical rings. This ring is not quite a cylinder. So X-rays will come in and hit the edge of this and bounce just a little bit. And then they'll hit the next one and bounce just a little bit more until they eventually are bounced down to a focal point. And here's what an entire X-ray mirror stack looks like. I think if you saw one of those sitting on a table, you would not say, oh, there's a telescope, but there's a telescope. Gamma rays are basically just energetic particles that hit the Earth's atmosphere and burst into a shower of what are they called, daughter particles. And so this kind of a telescope, it's just a light bucket. It just gathers light and is looking for those flashes as gamma rays disintegrate in the atmosphere. And I'm not sure what the angular resolution of this scope is, and really don't know much about gamma ray observing, but I thought that is a cool looking telescope. And it's designed for looking for the daughter particles of gamma rays. We get into, this is a tank underground in Japan full of water and millions of photodetectors. And what they detect when this is completely filled all the way to the ceiling with water, and they turn out the lights, what they're looking for is the flash of light when a neutrino hits a water molecule. And they can tell where it was in the tank by which detectors have detected a little flash of light. And as that streak goes through the tank, they know where the neutrino came from. And they can tell, when neutrinos have come from the sun. Back in '87, there was a supernova in the Large Magellanic Cloud, and they got a very clear signal through the Earth as the neutrinos came through and hit some water molecules in this tank. So that's a telescope. That is a weird looking telescope. Here's another telescope. This one's been in the news quite a bit lately because we're starting to really get some good data off of this. This is a telescope that actually is looking for gravitational waves by bouncing laser beams down these arms and looking for the interference pattern as the arms are actually compressed and stretched by gravity waves that come through. So, and again, we have 3 of them online, one in Washington, just north of us, one in Louisiana, and now one in Italy. And we're getting more of them online all the time. And as you get more telescopes, you get more resolution in terms of where the gravitational wave was coming from. And so we have actually been able to zero in on events, use optical telescope in the right direction and see an optical event that came along with the gravitational event. And we're seeing the merger of black holes and the collision of neutron stars using this telescope, which it may qualify as the most untelescope-like telescope imaginable, but there it is. So what's next? This is my last slide, and I am kind of thinking, well, maybe telescopes you don't even look through anymore. That's what both of these are. They're designed as consumer telescopes. They're a little bit overpriced right now, but the price will certainly drop. this looks like an eyepiece, but what it is a video screen that you look at through a magnifying glass. So you get the experience of looking through an eyepiece. But it has a primary mirror down here and a camera right there. Rather than a secondary mirror, it's got a camera. And that camera feeds the signal to this screen, and it will also feed the signal to your cell phone if you want. So you can gather images and you can do astrophotography with this telescope. And the Stellina, exactly the same thing. That's an 80 millimeter aperture there. This, by the way, is a reflector. This is a refractor. So you figure if that's an 80 millimeter aperture, that's actually fairly large. You know, this thing's bigger than my head. It doesn't have even the fake eyepiece. It just sends a signal to your phone or to your computer. And this seems to be pretty popular. People are buying these up. And as light pollution gets worse, I think we're going to see people using this kind of telescope more and more. It's totally computerized. It will find its own way around the sky. You just basically turn it on and give it a few minutes to find where it's pointed, and then you tell it what you want to look at, and it will go look at it. You know, in sky that's so light polluted that you can't see guide stars, that's probably the only way to go. So my guess is we're going to see a lot more scopes like this, and we're going to see a lot of variations on this kind of design. And this might be where telescopes go in the future. Or not, who knows? But that's my presentation on unusual telescope designs. Go ahead, unmute your microphones, ask any questions, throw out any comments you have, any speculation on what you think the future might be. Let's just turn this back into a free-for-all and see where it goes from here.
Any comments on Mersenne telescopes?
On which one?
Mersenne, I think it's like MERSENE.
I don't know anything about the Mersenne telescope. You tell me. What is it? What is it, and
Well,
how is it?
It's got like a mirror in the back, and it's got a concave mirror in the back like normal, and then a convex mirror up by sort of like a Cassegrain.
Okay.
Where it matches the curve of the primary mirror, so it returns a parallel light beam down the scope, and it can go out through a tertiary and a Naismith to the out through the altitude bearing, and then you have essentially another like a refractor or whatever to focus the light beam further to an eyepiece or camera, and which can be, and basically you can like look down into an eyepiece like you'd look down into a microscope.
Okay, so the end point is always going to be in the same spot, like an Naismith then.
Yeah.
Okay. Yeah, it sounds like it would be doable. It sounds like, you know, like with the Naismith or with the Coude, you know, you got all these reflecting surfaces, and none of them can be perfect. So I'm always dubious, you know, when you've got like 3 or 4 or 5 reflections, it seems unlikely that that's the optimum design, because you're losing light every time you have a reflection. But obviously, you know, it's useful in some situations for sure.
Yeah, there is a lot of light loss, I would assume. On the other hand, you know, you could have it project into, you could look down into an eyepiece that's in a dark room.
True. Yeah, you could be, you know, completely dark adapted while you're using that scope. Yeah. Anybody else got thoughts, comments?
Thank you very much. This is Bob. It was excellent.
Oh, thank you. Yeah, I enjoyed doing it, that's for sure.
Yeah, much appreciated.
Great.
Very good job.
Well, it's fun. You know, I write the column on amateur telescope making now for Sky and Telescope magazine, so I see a lot of weird ones. And, I write about the ones I think are really cool, but there's a lot of ones that it's like, well, it's weird, but not necessarily cool. but it got me thinking about, I should show some of these things to people and get an idea of how varied telescope design can be.
In World War II, the British had some audio telescopes that they used as an early warning system.
Audio telescopes, I suppose, sure, reflective.
Yeah,
parabolic dish to
big
reflect
parabolic
sound.
reflectors.
Yeah. I've seen something like that in science museums where you get all the way across the building and stand at the focal point of a parabola, and you can hear somebody clear over on the other end.
Yeah.
Thank you, Jerry.
Hey,
That was great.
Anybody else?
yeah, Jerry, it's Alicia. And Dan and I are wondering why we didn't see the scope you brought out on 4th of July.
Let's see.
The beanie weenie scope.
Yeah.
I didn't think
Are
to
you
put that one
saving
in.
that for a special event or something? I didn't want to spoil it, but
Oh, well, no. Let's see. Okay, you guys talk amongst yourselves. I'll go get it, and I'll show you this scope.
Okay, so who knows how to do card tricks? No one? Nope. At work, we're actually going to play virtual Pictionary next week, but unfortunately, I don't know how yet.
Here's a
Oh.
printed circuit board. That's the card I have.
There you go.
Okay, so here's the telescope they're talking about. I call it my Beanie Weenie telescope. It's a Maxitov built into a Bush's bean can. Let's see. Yeah, you can kind of see bushes there. And of course, the lens cap has to be tinfoil because that's what you put over a tin can when you put it in your fridge. And the bean can holds the optics, and then the dew shield is a Wiener wrapper around another bean can. But it's a Maxitov. I bought the optics. I did not actually grind the mirrors or anything myself. I bought the optics from Surplus Shed. And then I realized that it was the perfect size to fit inside a bean can. So there you go, my Beanie Weenie telescope.
that's awesome. Pretty
Beautiful.
weird.
The focuser is terrible. I still need to work on the focuser, but it's a work in progress.